Hi everyone, my name is Fatma. I am an assistant professor at Koç University in Istanbul. I'm sorry that I cannot be there. I would like to thank the organizers for the invitation and also for allowing me to record my talk. Finding objects on visual data is one of the oldest problems in computer vision. I guess we can all agree that we perfected it in the presence of labeled data. But what about when we don't have labeled data? Considering the variety of objects encountered in everyday life, there might be some objects that we don't have labels for. I'm going to talk about unsupervised discovery of multiple objects from videos. In the absence of labels, motion provides important cues to group pixels corresponding to objects. Obtaining accurate motion information may not be possible in some cases. Therefore, I will talk about a solution without using motion information in the second part of my talk. The existing solutions use motion either as input to perform grouping or as output to reconstruct as a way of verifying the predicted grouping. What is missing is the underlying 3D geometry that creates the observed motion that we see in the video. How can 3D help segmentation? Let's look at this scene and consider the possible set of motion patterns. Let's first consider a static scene case. Only the camera is moving, nothing else moves, so there are no independently moving objects. For this static scene, we can visualize optical flow with some false coloring, as you see here on the right. Optical flow describes the motion of pixels, a 2D displacement vector at every pixel. Here, color indicates the direction of motion, and the intensity is the magnitude of motion. Previous work asked a very interesting question. For a static scene like this, what is the space of all possible optical flow vectors? What do we need to know about the scene to obtain the space of all possible optical flow vectors? Again, nothing is moving other than the camera. If we know the scene structure, we can imagine the possible changes according to camera motion. But given the 3D geometry of the scene, that is depth at each pixel in this case, we can represent the space of possible optical flow patterns for that scene with only 6 flow bases. These are scene-specific flow bases that are derived from depth. I'm not going to go into detail here, but please check the amazing work below to see how to achieve this. But what about dynamic scenes with independently moving objects? Because scenes typically contain objects that move by themselves. In fact, multiple objects, as you see here in this video. This is an image from that video and the corresponding depth map. Let's assume we know where the background is. We define the background as the static part of the scene or the region that only moves according to camera motion. If we know which pixels belong to the background, we can do the same by masking out independently moving objects and obtain the bases only for the background. Specifically, we mask out everything else on the image and the depth, and then calculate the bases by only using the pixels in the background region. In fact, we can do the same for all regions on the image. For example, for the object in the middle, and create bases for that object. Combining bases for all regions, we can explain the motion in the whole scene, including background, foreground objects, one by one. But how do we get depth and segmentation? What we do is we train a segmentation network to extract each region for us, and a molecular depth network to obtain pixel-wise depth predictions. Using the output of these two networks, we create the flow bases which explain the motion in the scene. We assume that we have access to optical flow during training. It can be ground truth flow in the synthetic sequences, or it can be extracted using an off-the-shelf flow network such as Raft. Then we project the given optical flow to the bases that we estimated from depth and segmentation. What happens is that if our predictions are accurate, then the projected flow should be close to the input flow. For training, our objective is to minimize the distance between the reconstructed flow and the input flow. At inference time, we do not need flow. We can predict depth and segmentation from a single image. Therefore, our method is applicable to static datasets as well. We evaluated first on synthetic movie datasets. Movie datasets are commonly used for evaluating unsupervised object discovery methods. There are multiple partitions from A to E, and you see a sample from each here. Basically, there are multiple objects thrown into the scene, and the complexity increases as we go from A to E in terms of the number of objects, texture, etc. and the last one, E, movie E, also has camera motion. So here, quantitative results on movie synthetic data sets compared to some previous work. We show results with and without post-processing, where the ones with post-processing are marked with a dagger. So our results, even without post-processing, are significantly better than previous work on complex partitions C, D, and E. This shows that modeling 3D geometry works extremely well for segmenting objects on these synthetic data sets. The only exception is movie A. This is because there is not enough texture to predict accurate depth on movie A. In the ablations, we found that only rotational motion without translation achieves state-of-the-art on movie A. Here are some qualitative results where each instance is colored with a different color. Our method can segment objects reliably by using depth information. We also performed experiments on real data, DynaVis 2017. Here we extracted flow using Raft. There are two versions of our model. Ours M basically uses ground truth information for the number of objects. This is to handle the over-segmentation issue. So on DynaVis 17, our method is the first to obtain state-of-the-art performance without using motion information at test time. Some qualitative results compared to Oculier, which relates flow from multiple frames. As you can see, Oculier fails when flow estimation fails, like in the karate case or the swan, or when the objects are static, like the bike. Our method does not rely on flow for inference, therefore it does not suffer from these issues. We also have some impressive results on Kitty. What is more impressive on Kitty is that we can obtain accurate depth predictions with comparable performance to state-of-the-art in molecular depth prediction. So let's move on to the second part. We had some impressive results on real data sets where we can obtain accurate flow for training. But what about when we don't have accurate flow information for supervision? This is the case on YouTube videos. These in the wild videos that you see here are pretty challenging for optical flow estimation due to deformable objects, changing lighting conditions, past camera motion, and so on. Moreover, there can be some static objects which will be ignored by a segmentation network relying on flow as input. Actually, it's not only flow. Previous work relies on other modalities as well, such as motion segmentation or sparse depth, which might be available in driving domain from sensors like LiDAR. However, these methods are typically evaluated on synthetic data sets or in restricted domains and fail when applied to in the wild videos that we saw previously. There is a line of work called object-centric methods, which first divides the input into a set of slots to create a bottleneck, and then reconstructs the input from these slots. Each slot binds to distinctive parts corresponding to an object. There are several work based on slot attention like that, and they typically reconstruct the pixels. And recent work here that you see, Dinosaur, showed that we can obtain better performance by performing reconstruction in the feature space instead of pixel space, basically by using Dyna features, hence the name Dinosaur. This way, we can apply slot attention to in the wild images and segment multiple objects, as you see here. So Dinosaur is an image-based method. It does not make use of temporal information. And the video-based ones require an extra modality and fails in generic videos when we cannot extract that modality reliably. So we ask the following question. Can we do better in videos by applying the findings of Dinosaur to videos, but also by utilizing the temporal dimension which is available in the videos? So we introduce Solve. Solve is an object-centric framework for instance segmentation in real-world videos. Our input is a temporal window with some frames, and our goal is to reconstruct the central frame in this temporal window by doing the same thing Dinosaur does, in the feature space, basically. So we will use an object-centric representation with slots, and our input is a set of frames in a video. So for encoding the frames, we use the frozen Dino version 2 architecture, and we drop some ratio of tokens randomly to reduce the memory footprint. Given the mask feature maps, we extract slots of each frame independently with our spatial binding module. Here, we utilize invariant slot attention by initializing it with shared and learnable parameters across frames. This is to encourage slots with same index to bind to the same object region across frames. Then we relate slots across time in the temporal binding module. what we do is we apply temporal attention to the slots with the same index across different time frames. Each slot learns about its future and past in the temporal window. This way, we can learn temporal representations of objects. So in slot attention, we have a fixed number of slots. Therefore, typically slot attention approach suffer from overclustering issue. Good news is that when we look at the similarity matrix of slots, we see that pixel embeddings from the same object are closer to each other than those of different objects. So we can simply merge slots using agglomerative clustering. Why agglomerative clustering? Because we don't need to know the number of clusters. We first compute the affinity matrix between all slots based on cosine similarity, and then use this affinity matrix to cluster slots into groups. Finally, we decode the merged slots to segmentation masks. Specifically, we use an MLP-based spatial broadcast decoder. Overall, our pipeline looks like this. Our model reaches the state-of-the-art performance on the most challenging synthetic MOVE dataset, and this is important, without using an extra modality at train or test time. More impressively, we can apply our model to real videos of UTUVis and obtain impressive performance. Ocular here uses flow from multiple frames and fails on UTUVis when the flow information is not reliable. We also evaluate on DynaVis 17. Here we are behind Ocular. The reason is that we can obtain more accurate flow on DynaVis 17 compared to UTUVis due to the less complex videos. Here we see some qualitative results which show segmentation of both rigid and deformable objects. Again, results showing multiple deformable objects on the left and deformable and rigid objects together on the right. So more results with cute animals moving like a lot. Thank you for listening. If you have any questions, feel free to send me an email. Also, you can follow me on Twitter for more research updates from our group. Thank you. Enjoy CVPR.